Hi everyone. In this lecture we're going to talk about chi-square analysis. And similar to the other inferential tests that we've gone through this semester, we're going to start off with when to use chi-square analysis when it's appropriate. And then we're going to focus primarily on the one type of chi-square test that is most commonly used in our field, which is known as the chi-square test of association, other times referred to as the chi-square test of independence. We'll walk through an example using that particular test, and then we'll walk through a second example. The readings that correspond with this particular lecture are chapter 10 and the pages that you can see on your screen. So let's go ahead and get started. So when do we want to use chi-square analysis? This test is going to differ from the other inferential tests we've talked about this semester. So you may recall that whether it was the t-test or the ANOVA f-test or even linear regression analysis, in each one of those particular inferential tests, a key thing was that the dependent variable, the outcome variable, had to be continuous. It had to be at that interval or ratio level of measurement. In chi-square analysis, it's different. Chi-square analysis, all variables in the analysis must be categorical. So both the independent variable as well as the dependent variable must be categorical, meaning that they are at the nominal or ordinal level of measurement. The first type of chi-square analysis is known as the goodness of fit test. Now we're not going to actually walk through SPSS analysis for the goodness of fit test. We're not actually going to go through it and any specific examples in any more detail than what you see on this particular slide. But by looking at the goodness of fit test, it gives you a good opportunity just to sort of see how the chi-square analysis works. What's the mathematics going on behind the scenes? So for a goodness of fit test, you start with only one variable in the analysis, and that one variable must be categorical. It must be nominal or ordinal level of measurement. And you may be asking yourself, well, what kind of hypothesis test or test can I do with only one variable? Well, what it's doing is it's evaluating whether or not the observed frequencies of occurrence across the various categories of this one variable fit the hypothesized or expected frequencies. And as you'll see both with the goodness of fit test as well as the test of association that we'll get to on the next slide, one of the sort of the mechanics behind the scene with chi-square analysis is this comparison of what are known as observed frequencies versus expected frequencies. So let's take a look at this example of how a goodness of fit test works. So on the bottom of the screen, we see an example that starts off with a setup. The maker of a popular candy claims they produce an equal percentage of all four colors of their candy: orange, green, red, and blue. So once again, the one single variable is the candy or candy color, right? And that one single variable, candy, has four different levels or four different categories to it, right? And those represent the different colors of the candy. So level 1 is orange, level 2 is green, level 3 is red, and level 4 is blue. So 4 levels, 4 categories for one categorical variable, which is candy. And if the makers claim that they produce an equal percentage of all four colors of their candies, if you were to find a big vat of these candies and go through them, what would you expect the color breakdown to be if the maker's claim was accurate? Right? So if there's four different candies and the claim is that there's an equal percentage of all of them, then you would expect 25% of the candies in a particular batch to be orange, 25% to be green, 25% to be red, and finally 25% to be blue. So that's how we sort of set up the idea of the expected frequencies, right? And as you'll see on the next slide, the expected frequencies are also sort of synonymous with our concept of the null hypothesis, right? This is sort of the normal. What's out there is expected to be normal. Would be 25% for each one of these different types of candies. So then let's move to our sample. A researcher goes out there and collects a simple random sample of 200 candies. And once they get these 200 candies, they count each one and sort them out into the different types of colors, and it produces the following distribution that we see at the bottom of the slide. These give us the observed frequencies. So out of the 200 candies total, 64 of them happen to be orange, 42 of them happen to be green, 38 happen to be red, and 56 happen to be blue. So when we convert those into percentages, we see that 32% are orange, 21% are green, 19% are red, and 28% are blue. All right, so that's our setup for a goodness of fit test. And so now let's go back to this idea of what I started with, the comparison of observed frequencies versus expected frequencies. We can see, let's just look at the orange. The expected frequencies for orange are 25%. But our actual sample is not 25%, right? It's 32%. So it's a little bit, our observed frequency is a little bit higher than the expected value. Let's look at green. Green, the expected was 25, but our observed was a little bit lower at 21. And we can see that for both the red and the blue, they're also a little bit different from the expected frequencies. Well, that's sort of what the main question comes down to with the goodness of fit test or a chi-square analysis is, are those differences in our sample data enough for us to conclude that there is a significant deviation from the expected frequencies, right? And we know we're working with a sample of only 200 candies, so we know there's going to be, it's not going to be a perfect reflection of the expected frequencies, but as with all the hypothesis tests we've done before, we need to actually run the statistics in order to see whether or not our data deviate enough from those expected or null values for us to actually claim that there is some sort of statistical significance. So that's where I'm going to end with the goodness of fit test, but I just wanted to sort of show this one to illustrate the concept of observed versus expected frequencies. Now we're going to move into the more commonly used chi-square test, which is the test of association, and that's the one that we're actually going to be using SPSS data, and we're going to be walking through some examples that are relevant to our course. So let's go ahead and shift over to those. The second type of chi-square analysis is known as the test of association or the test of independence. And this chi-square analysis requires two variables, so two variables being compared in order to assess whether or not there is a significant association between those variables or to assess whether or not those two variables are independent of one another. So similar to what we started with the concept of chi-square in the previous slide, even though we now have two variables, both of the variables, the independent variable and the dependent variable, must be categorical. So they must be at that nominal or ordinal level of measurement. When you're working with chi-square analysis, no matter what type of chi-square analysis, you do not use continuous variables. You only work with categorical variables. So real quick recap, test of association examines the association between two variables where both the independent variable and the dependent variable must be categorical. And the test itself is actually examining whether or not there is a significant association between those variables. And the focus of analysis, and you'll see this when we look at some of the SPSS output, is still on differences between sort of the observed frequencies, what our sample actually gives us, versus those expected frequencies, so those sort of those null value frequencies. And the first example we're going to walk through for this one, we're going to look at the association or potential association between two categorical variables. The first variable will be gender, and in this particular study we can imagine that gender was measured in a dichotomous fashion with simply a male category and a female category, so categorical with two levels or two categories. And the second variable, crime type, is also measured in a categorical fashion but with three levels: violent, property, and drug. And if we were to set up the actual formal hypothesis testing steps, and we're not going to go through all the hypothesis testing steps that we've done in previous inferential tests, but if we were trying to get an idea of like what are the two competing hypotheses that we're testing here with this test of association, we can look down at the bottom of the slide and we can see that the null hypothesis would be written something along the lines of there is no association between gender and type of crime committed. versus that research or alternative hypothesis H1, which would be there is an association between gender and type of crime committed. Data for a chi-square test of association are often initially presented in what is known as a contingency table, otherwise known as a cross-tabulation table. And that's what we see on this particular slide for our gender by crime type example. So what we see, let's take a look at the various cells and pieces of this table. If we look to the far left, the first column heading that we see is gender, right? So gender represents one of our two variables that we're analyzing. If we go down that column below gender, we see the two categories of that particular variable. We have the male and then we have the females. And then if we move a little bit to the left in the table, we see that the next major column heading is crime type, our second variable. And right below crime type, we have the three different categories of that particular variable. We have violent, we have property, we have drug. With that cross tabulation of gender by crime type, what we create are sort of the 6 primary cells of our contingency table. And those are the cells that have more of a gray look to them. So let's take a look at what's in each one of those 6 important cells for us. So let's look at that where male and violent come together. And that still has the extra information about observed and expected. The top number provided in each one of those cells is the actual observed frequency, the observed count that we got within our sample data. So when we try to figure out how many male offenders who were convicted of violent crimes were in our sample, we look to the male violent box and we see that observed value of 48 individuals. If we go right below that box to the female violent, you'll notice that the top number is 5. So that means we observed 5 females who were convicted of violent crimes. Now the second, or the lower number in each box, is the expected frequency. So once again, going back to the male violent offenders, we see that the expected frequency was 42.0. If we go to the box below it for females, the expected frequency of females who are violent is 11.0. And what the chi-square analysis is going to do is it's analyzing the deviation or the differences between observed and expected frequencies across the entire contingency table, across all 6 important cells of that design. The more that the observed and expected frequencies differ from each other, the more likely it is that there is a significant association between these two variables. And conversely, the more that the observed and the expected frequencies are closer to one another, the less likely that it is that there's a significant association between the two variables. Now, in this particular study, we have 6 sort of important cells, right? We have the male violent, the male property, the male drug, the female violent, the female property, and the female drug. What I call the action as far as determining significance or non-significance doesn't have to occur in all 6 cells. It can only be, 2 or 3 cells where we see a really large difference between observed and expected values that may push our statistic towards statistical significance. So even though if we look at, say, for example, the male drug offenders, the difference between observed and expected is just roughly over 1 person, right? 75 versus 73.7. The same thing holds true in the female drug offenders, where the difference is just over 1, right? 8 and 19.3. So there's not much of a difference between observed and expected frequencies in that particular portion of the analysis. But in other cells, you see a larger difference between observed and expected frequencies. And that's where we leave it up to the actual chi-square statistic and the actual statistical analysis behind the scenes, the mathematics, to determine whether or not, at what point do we have a significant amount of difference between those to say that we have a statistically significant association between the variables. Now, the final thing I'm going to go through is sort of remind us of where those expected frequencies came from. How did they originate? How did that 42.0 for male violent, that 11.0 for female violent, etc., come from? You may recall expected frequencies are what we often call the null value, saying that there's no association. The way that they are computed for a chi-square test of association is based upon the overall sample information, but primarily focusing on what we call the row totals and the column totals for each particular cell. And the way that they're computed is you take the row total times the column total divided by what we call the grand total. And the grand total just means the overall sample size. So if you look down to the very low right-hand corner of this contingency table where the row total column and the column total row sort of meet together, you'll see that value of 250. 250 is the overall sample size for our study. So if I wanted to compute the expected frequency for the males who are violent, I would take the row total for the males, which is, if we look at the male, go all the way to the right to the row total, we see 198. Multiply that by the column total for violent. So I'd look at violent, go all the way down to the bottom to the column total, I see a 53. I do 198 times 53. Get an answer, divide it by the grand total of 250, and that's where that expected total of 42.0 came from. And you could go through and see how that matches for each of the expected frequencies throughout this contingency table. So that's just sort of a glimpse at the mathematics behind what's going on in a contingency table and sort of this comparison between observed and expected frequencies. So let's go ahead and jump ahead to looking at what SPSS presents for us when we run a chi-square test of association. So what we have on this particular slide are two of the key elements of the chi-square test of association, that the output that SPSS produces. The top table that is produced says crime type by gender cross-tabulation. This contains the exact same information that we saw on the previous slide. The only thing that I've changed is which variable encompasses the rows and which variable encompasses the columns. I did this once for display purposes, but also to show you that the overall outcome will be the same. And in fact, if you go back and look at the male violence, you look at the observed versus the expected frequencies and go through each of the 6 cells of the design, you'll notice that the numbers in this top table match exactly what we saw on the previous table. Another reason why I set it up this way for SPSS is sort of the general agreement in the field when you're entering your data and your variables into SPSS for a chi-square analysis, is that your independent variable is typically inserted into the column section, and then your dependent variable is inserted into the row section. So that's why we think about, if we're looking at the association between crime type and gender, we have to think, well, what came first? Did your crime type determine your gender? No. More often than not, we would probably argue in a logical fashion that maybe there's an association between your gender having an influence on your crime type. So we identified gender as our independent variable, so it became the column, and then crime type becomes our dependent variable, so it's inserted into the row. The other slight difference that you'll see with this cross-tabulation table is, instead of calling some of the numbers observed frequencies and then the other ones expected frequencies, the way that SPSS output will display them is the observed frequencies are called count, and you'll see that in that table, while the expected frequencies are called expected count. And so you notice they don't have them in percentages, they're just in raw numbers from the actual data. But other than that, the material is there. So let's go ahead and jump down to the bottom table, the one that's labeled chi-square tests. This is where we finally start to get our answer to our hypothesis test. Is there an association between gender and type of crime? Now, although chi-square tests are considered non-parametric tests, and you go back in your notes to the beginning of the semester, you may recall how we talked about parametric inferential tests that make assumptions about the distribution of the phenomenon, etc., while non-parametric tests do not make assumptions about the distribution of the phenomenon. Although chi-square tests are technically called non-parametric tests, there is sort of one assumption, if you want to call it that we as researchers need to check. And that is the assumption of expected cell frequencies. So make sure you're paying attention to what I'm about ready to say right here. In order to make sure that a chi-square test is valid, first of all, we have to make sure that our variables are appropriate. So for a chi-square test of association, both our independent variable and our dependent variable must be categorical variables. We mentioned that earlier. But a new one that we also have to make sure of is what we call the expected cell frequencies count. In order for chi-square tests to provide valid findings, we need to make sure that none of the expected frequencies are less than 5. So I'll repeat that one more time. In a chi-square test, none of the expected frequencies should be less than 5. And in fact, this assumption is so important that SPSS will automatically give you a footnote that you can see down there as footnote A below the chi-squares test table that tells us the answer about whether or not we met the assumption of expected frequencies. And in this case, we did. We're in good shape. You'll notice that footnote A says 0 cells have expected count less than 5. That is what you want to see as a researcher. If you have one or more cells that have expected counts less than 5, then you need to rethink whether or not a chi-square test is appropriate for your data, or whether or not perhaps you need to collapse categories. So say you had, 3 or 4 categories for one particular variable. Do you need to collapse those into only 2 categories or something like that in order for the mathematics to end up with expected counts that are all of a value of at least 5? So once again, that in this case, we're good to go. That assumption of expected cell frequencies, we have met the assumption because 0 cells have expected counts less than 5. So we can go ahead and move on to our chi-square results. So although there's more information in the chi-square test box than you probably need, at least for the sake of this course, the most important information is that Pearson chi-square row of information. So the chi-square statistic, as you'll see over here in red on the right side of this slide, chi is written almost with the Greek letter chi, so it looks kind of like a fancy X when we're writing it out, and it's squared. And so the value of it is simply, it's referred to as the Pearson chi-square. So the value for our chi-square statistic is 7.443. Similar to other tests that we've worked with this semester, we also need to report our appropriate degrees of freedom. For the chi-square test, we only need to report 1 degree of freedom, and it's right next to the Pearson chi-square, and it's on that DF column, and it's a value of 2. And then finally, we need to know our significance or our p-value. And it's a 2-sided test, so you look at that column that says asymptotic significance, 2-sided, and you get the p-value of 0.024. So we put that all together, and I have it sort of written out there in red on the right side of the slide where we have the chi-square results. Our chi-square with the degrees of freedom of 2 equals 7.443 and an associated p-value of 0.024. Because that p-value is less than 0.05, right? 0.05 is our standard starting point, our standard alpha. Because the p-value of 0.024 is less than 0.05, we can reject the null hypothesis and conclude that yes, there is a statistically significant association between gender and crime type. And that's it. Now, on the next slide, we're going to look at one extra piece of information that we often like to report with chi-square tests. So let's go ahead and look at that piece too. Here is the third box that is of importance that is produced by SPSS output. And this is what is known as the effect size. And this will show up in your SPSS output as the symmetric measures table. And you'll notice that there's two measures of effect size in this particular box. So if we look at the row, it says nominal by nominal. So once again, that is just SPSS assuming that both of our variables are at that categorical level of measurement and are in fact nominal. So it's nominal variable by a nominal variable, and we have two different measures of strength of association or effect size. And these are phi, PHI, as well as Kramer's V. Now, many textbooks will refer to phi as being sort of your starting point for a chi-square. And in fact, you'll notice that the values produced in this particular example are the same for both phi and Kramer's V. I tend to lean towards always reporting Kramer's V because, one, in a simple chi-square like this one, where you only have, 3 levels of one variable, 2 of the other, they're the exact same value. But as the number of levels or categories for your variables increases, say you had one variable that had 3 levels and a second that had 4, or, another analysis where you had your first variable had 4 levels and the second had 5. As the number of levels or categories increase for your independent and dependent variables, the values of phi and Kramer's V will start to differ. But Kramer's V is always going to be a more conservative estimate of the effect size or the strength of association between the two variables, and therefore is often used as sort of the go-to catch-all. So I tend to encourage students to report Kramer's V whenever you run a chi-square test. And all you have to do is report it. You look at Kramer's V, you look at the value, you see a value of 0.173, and you report it. Sometimes there's an argument for squaring that value, similar to what we saw with R and R squared for that coefficient of determination back when we talked about the Pearson correlation coefficient. And there's different times and rationales for why you would leave it in its raw state versus squaring it. For this point in this course, I just want you to be able to know to recognize it, that it is an important piece of output for us to report. And similar to other measures of strength of association or effect size, there are breakdowns that are provided in various statistical textbooks that talk about what we would call a small effect, a medium effect, a large effect for Kramer's V. I'm not going to have us dwell on that too much because, once again, as is the case with a lot of effect size measurements, it depends upon the nature of the data and the variables that you're working with. I think it's important for us right now just to know that we should report it and then let our readers interpret and understand it and do with it what they might. And especially with chi-square, one final note on this, it's really important to include a measure of effect size whenever you're running a chi-square analysis, because one of the shortcomings of chi-square is that the analyses using chi-square are often highly influenced by sample size. So what I mean by that is if you have a really large sample size, say in the multiple hundreds or multiple thousands of cases, your likelihood of getting a significant p-value, like we saw in the previous slide, goes up pretty quickly. Chi-square, more so than other tests, is heavily influenced by sample size, and therefore do we not only want to report whether or not we had a statistically significant finding based upon the p-value, but we like to give sort of a backup estimate of just what was the strength of association between the variables being analyzed, and that's where Kramer's V comes into play. So that's it for chi-square. If you can understand what we've sort of walked through with the example of chi-square test of association, how to look at these 3 important boxes in the SPSS output, how to check that expected cell frequencies, how to find the p-value for the chi-square, as well as the Kramer's V as a measure of effect size, you're in good shape. But I'm still the last couple slides, we're just going to walk quickly through one more example just to sort of show how it might look with slightly different data and slightly different variables. In this second example, we once again have 2 categorical variables. We still have crime type, which is one of the variables that we used in the previous example that has 3 levels, and it's at that nominal level of measurement where we have crime type broken down into violent, property, and drug as the 3 categories or levels of it. And then our other variable that we've introduced here is criminal history. Criminal history is also categorical, but we'd probably argue that it's more at that ordinal level of measurement. But because it is still categorical, it's still technically okay to use chi-square analysis. And criminal history, and this one has 3 levels to it, where it is measured as a first-time offender, an individual with 1 prior offense, or individuals who are what we would call repeat offenders who have 2 or more prior offenses. We see in the top table that in the cross-tabulation table, we see a breakdown of the 2 variables as well as the observed and expected frequencies or counts within each cell of the design. And then we can jump down to the chi-square test box to see whether or not first, do we meet the assumption of expected cell frequencies? And sure enough, also in this example, we see that that footnote says 0 cells have expected count less than 5. That is a good sign. That means we can use chi-square analysis. Then in order to interpret our chi-square results, we look at the row of information from the Pearson chi-square row, and we notice that the value of chi-square itself is 5.081. The degrees of freedom in this particular analyses are 4. And we have that written out. And then in this case, our p-value is 0.279. Now, because our p-value is greater than 0.05, we fail to reject the null hypothesis, and we would conclude that there is not a statistically significant association between criminal history and crime type. And finally, we have our symmetric measures or effect size measures box. And once again, we would report the Kramer's V. And the Kramer's V, you'll actually notice, perhaps it's not surprising that it is a little bit smaller than the one that we saw in our previous example, but also you may recall that in this one, we didn't have a significant finding, so that sort of is indicative of that. Our Kramer's V value here is 0.113, so we should go ahead and report that with our findings. But also one thing that you'll notice here is because both of our variables, both our independent and our dependent variable, had 3 levels. This is what I was getting at before, whereas this is where you start to see how phi and Kramer's V will not always be exactly the same. As you start to add more levels to the particular variables, you'll see the values of phi and Kramer's V differ, and in fact Kramer's V is a lower value because it tends to be what we call more conservative, and that's why I often lean towards reporting that one instead of the phi value. So that's it with chi-square, and specifically with chi-square test of association. I hope you enjoyed this lecture, and I hope it made pretty good sense to you, and take care.